These are the lecture notes for Chapter 2, Part A. We're starting at the beginning. This is the chapter on basic chemistry and organic chemistry. I will try, I say organic chemistry, biochemistry. There's a lot of different words, but mainly you can look at it as the chemistry we need for anatomy and physiology. So, and I'm sorry, I know I sound stuffy. I've had COVID, but I still want to get these lectures recorded for you. So I hope that you can understand me pretty well, and I will do the best that I can. So section 2.1 is on matter and energy. More than likely, it's a review for most of you from high school science, most likely. Matter is defined as anything that has mass and occupies space. So mass and weight are very similar. Weight is just mass plus the effects of gravity. Mass is the same on the Earth and the Moon, and weight is different. Weight is less on the Moon. And then for occupies space, it just means that all matter has a volume that you can measure. The states of matter are solid, liquid, and gas, and they don't have listed here plasma, which is found in the sun and other stars. Energy is defined as the capacity to do work. The more work that is done, the more energy is used up. There's an animation, and this is from, slide number 9. If you would like to watch it. I don't ask a lot of questions on energy. We just kind of have to cover it. So if you would like to watch it, it's slide number 9, and it's short. But I will tell you how or explain the two different types of energy and how they how we use those or study those in anatomy and physiology. So kinetic energy is energy in action. You may have learned it as the energy of motion, and potential energy is stored or inactive energy. We're going to notice potential energy, or we're going to study it as energy that is stored in chemical bonds. And kinetic is going to be energy that's released during chemical reactions. Now, we do see kinetic energy released in the form of muscle contractions, for example. That would definitely be the energy of motion. But mainly potential we're going to see stored in the bonds of chemical substances. So we call that chemical energy. Electrical energy is a form of kinetic energy. It results from the movement of charged particles. We also call it electricity. And mechanical energy is directly involved in moving matter. So when our muscles contract and cause our bones to move, that's going to be mechanical energy. And radiant or electromagnetic energy are the various forms of radiation that we see in the electromagnetic spectrum. Some of them are listed here: heat energy, visible light energy, ultraviolet light, X-rays, gamma radiation, and we may convert, or energy may be converted from one form to another. If we turn on a lamp, that converts electrical energy to light energy. And every time energy is converted, this energy conversion is inefficient. So we always lose some energy as heat to the environment, and we can't really use that energy. So that's why we say it's lost. It's really not lost. It's just lost to us. Now, moving on to section 2.2, we use a lot more of this information in biology and A&P. So all matter is composed of elements. These are the pure substances that you find on the periodic table. They can't be broken down into simpler substances. And the smallest particles of elements are atoms, which we'll find on the next slide, I think. You do need to know the 4 elements that make up 96% of the human body, and they are carbon. The symbol for carbon is a capital C. Oxygen, the symbol is a capital O. Hydrogen, capital H. Nitrogen, capital N. So they're pretty easy to remember. There are 9 elements that make up almost 4% of the body, and then 11 that make up less than 0.01. Again, elements are made up of atoms, and they're the building blocks for each element and the building blocks for molecules. The atomic symbol that I just mentioned to you, oxygen is O, carbon is C. Some symbols are 2 letters. I think there may even be a few that are 3 letters. In fact, I know there are some of the more not as common, not as well-known elements. But some of the symbols come from the Latin names of the words for the elements. So we say sodium, but the symbol is capital N little a because the Latin word for sodium is natrium. Potassium, for example, is a K because the Latin word for potassium is kalium or kalium. I'm not sure. Anyway, here are the symbols for the 4 elements that make up 96% of our body. They're O for oxygen, C for carbon, H for hydrogen, N for nitrogen. You can see the percentages listed here and some examples of where you would find those elements. These are the elements that make up about 4% of the human body, and they're calcium, Ca, phosphorus, P, potassium is K, sulfur is S, sodium is Na, chlorine is Cl, magnesium is Mg, iodine is I, and iron is Fe. So these are found, for example, calcium is stored in our bones, but it's very important in muscle contractions. When your blood levels of calcium are too high or too low, that can lead to your muscles either staying contracted and they won't relax, or staying relaxed and they won't contract. In either case, you become paralyzed. That means not only can you not move, but you can't breathe. Your heart can't function, so you die. So the levels of calcium in our blood are very, very important. And that's why we're going to talk about how our body maintains those levels. Potassium levels and sodium levels are very important for muscle contractions and nerve impulses. Magnesium levels are important for absorbing vitamin D and calcium. And then iodine is important in thyroid hormones, and iron is important in transporting oxygen. Now, we also have some trace elements, and a lot of these are minerals, chromium, cobalt, copper, fluorine, manganese, molybdenum, selenium, silicon, tin, vanadium, and zinc. You don't have to memorize those. The only ones I want you to know are the 4 most common ones: oxygen, carbon, hydrogen, and nitrogen. You'll learn the others as we go, as they become important in what we're learning. Now, we do need to talk about the structure of atoms and the subatomic particles that are found within an atom. Make sure you know the charge and the location of each of the particles. Protons have a positive charge. They're located inside the nucleus of the atom. Neutrons are neutral. They have no charge or 0 charge. They are also located in the nucleus. And electrons have a negative charge, and they are found outside the nucleus in electron clouds. We're looking here at a picture of 2 different models. I think for our purposes, the planetary model is more useful. It shows that there are 2 protons, they're shown here in red, in the nucleus of this particular atom. there are 2 neutrons in the nucleus, and then there are 2 electrons in the first electron shell. This is the model of a helium atom, and we know that because helium has an atomic number of 2. The atomic number is always the number of protons in the atom. The atomic number, and the atomic number, or which is also the number of protons, will never change for an atom. So if an atom has an atomic number of 2, it's helium. If that atomic number changes, it is no longer helium. So if it loses a proton somehow, it becomes hydrogen. So the atom is defined by its number of protons or its atomic number. Now the mass number for an atom can change because the number of neutrons can change. So the mass number for an atom is equal to the protons and the neutrons in its nucleus. So helium has 2 protons and 2 neutrons, so its mass number is 4. And then isotopes are the same atom that have different mass numbers, or you could also say they have different numbers of neutrons. The most common form of hydrogen has 1 proton, 0 neutrons, and 1 electron. But the isotopes of hydrogen are deuterium, which has 1 neutron instead of 0, and so its mass number is 2. And another isotope of hydrogen is tritium, which has a mass number of 3 because it has 2 neutrons plus the proton. Going back to the definitions real quick, the atomic number is the number of protons in the nucleus. The mass number is the number of protons plus the neutrons. So when you look at a chemical symbol, let me see if I can find one. They don't have one. Great. Okay, so I will try to write one for you. Or let's just... Okay, let's just use lithium. Now, I warn you, my writing is terrible, and especially when I try to do it this way. But lithium, the chemical symbol is, see what I mean? Is Li. Let me try one more time. Okay, and you're going to see the smaller number is the atomic number. So the atomic number for lithium is 3. And then the larger number is the mass number. The mass number for lithium, you can see it has 3 protons and 4 neutrons. So the mass number is 7. That's supposed to be a 7. I'm not doing that again. And I'm sorry, I don't have a better way of doing this, but it should be capital L, little I is the symbol, and then 3 is the atomic number, and 7 is the mass number. All right. And sometimes you'll see like here, okay, they just aren't writing it where you see both of them together. Here you see the atomic number on the bottom and the mass number on the top. That doesn't really matter. I see it both ways with the atomic number on top, mass number on bottom. Just make sure if you see the symbol of any of the elements and you see 2 numbers, the bigger number is the mass number and the smaller number is the atomic number. Isotopes are defined as atoms whose atomic numbers are the same, so their number of protons never changes, but their mass numbers are different because their numbers of neutrons are different. We just went over that with hydrogen. And then some isotopes give off radiation. They're called radioisotopes because as they decompose, they do release radiation. We can make use of radioisotopes in biological research and medicine, and we do make use of radioisotopes. Sometimes, well, I don't see any examples listed here, so I'll just tell you. We use radioisotopes as a tool to image certain body parts. So a PET scan uses radioisotopes, and a thyroid scan uses the radioisotope for iodine. You would have to be injected with iodine, and then your thyroid gland would absorb that iodine because it uses iodine to make its hormones. And so everywhere in a scan, you would see your thyroid gland, and whether or not it's enlarged, whether or not you have a goiter, whether or not you have a thyroid tumor, that kind of thing. So radioisotopes can be used to do images of the body to help diagnose disease, and they can also be used as a tool, for example, in radiation therapy for cancer. And then sometimes they cause cancer. I'm going to stop here. We'll start with the next recording, section 2.3, combining matter, so compounds and molecules.